So let's look at some examples of how we would find a derivative bringing into play some of these properties here. Well, let's look at some examples. So let's suppose we've got y equals, let's say 3x to the 5th, something like that. Well, this is a straightforward power rule here. And we've got the constant. So what we have here is we're going to have 3 times 5x to the 4th. See? Notice how I just said, okay, I'm just going to go ahead and differentiate this x to the 5th using the power rule. See? The power rule right here. And then I'll multiply by the constant. So this is going to be 15x to the 4th. Now you don't have to think of it that way. You don't have to think of it as, I'm factoring out the constant and then differentiating. You could just say, well, I'm going to say 5 times 3. Just go ahead and do that. 5 times 3 is 15, x to the 4th. You could do that. Okay, let's suppose that we've got y equals x to the 3rd plus the square root of x, something like that. Okay, now we can differentiate straight across here. And this is going to be, this is like one function plus another. Well, just differentiate straight across. So we've got dy dx is equal to 3x squared plus, how do we deal with this x to the, the square root? Well, we can recognize that as, and before we differentiate, we should go ahead and convert it to this fractional exponent. See, because, when it's in this radical form, we can't really do anything with it. But when we view it as a fractional exponent like this, now we can use the power rule. See, this is going to be 1/2 x to the 1/2 minus 1. See, there. So that's the key here. So whenever you see a radical like that, first thing you do before you plunge in and start differentiating is convert it to the fractional form. So now we have this. We have 3x squared plus 1/2 x to the negative 1/2. And I'll just leave it like that. Okay? But that's the way we can do it. Okay? Now, let's suppose that we've got y equals, let's suppose we've got the cube root of x squared plus x to the negative 3. Something like that. Okay? Well, here we go. dy, whoops, before we do that, before we start trying to differentiate, let's go ahead and see what we've got here. We've got y equals, let me see here, this is x to the 2/3 power, right? That's what that is. The power goes on top and the root on the bottom, right? Plus x to the negative 3. Now that we've got those radicals gone, that radical gone, we can differentiate. So this is dy dx is equal to 2/3 x to the 2/3 minus 3/3, minus 1, plus negative 3 x to the negative 3 minus 1. Okay, so let's see if we can clean that up a little bit. We've got 2/3 x to the negative 1/3. Yeah. Minus 3x to the negative 4. Now remember to be careful when you're trying to differentiate with these negative exponents using the power rule, because the tendency would be to call that a negative 2. But no, a negative 3 minus 1 would be a negative 4. So you just have to really be careful there. Okay? Now, let's look at this one. Let's suppose we've got x to the 5th plus 2x to the 3rd plus, let's say x. And let's suppose we're dividing that by x. So now we have this quotient here. Well, and it doesn't look like any of our properties will work on that, right? We don't have any properties for quotients this way. However, if you view it this way, if you view this as x to the 5th, notice this is just over one term in the denominator, so we could split this up this way. Yeah, we can split it up that way. Now this is something that we can handle, because now what we have is we have y equals x to the fourth, see, that first one, plus 2x squared, see that, 2x squared, plus 1. Now, this is no problem for us. dy dx would be equal to 4x cubed, see that first term, plus 4x, see the second term, and the derivative of 1, well, that's just 0, okay? It's saying, you know, a constant doesn't change, so you can't measure the change. The derivative of a constant is 0. I mean, you can measure it as 0, but it's pretty simple. Okay, so there's some basic examples of how we can use these properties.